Hi, welcome to this video. And in this video, I'm actually going to talk about carbon versus gold electrodes in electro-analytical chemistry. So electro-analytical chemistry, electrochemical sensors, electrochemical biosensors, etc. Point of care diagnostics, maybe continuous monitoring. With that said, let me jump into this kind of comparison of these two materials. Now, I'm not only going to compare these two materials technically, but I'm also going to compare them commercially. So I've got a bit of a table here, but let me go through it in a kind of, I'll go through it and call out what I mean by behind each kind of entry. So as I say, I'm going to look at gold versus carbon electrodes for electroanalytical chemistry. And the first thing I'm going to kind of touch upon is when I say gold versus carbon, so I really want to touch upon the elephant in the corner here, which is expense. So for example, if I hold up this carbon electrode here, this is one of our carbon 501s, it's a fraction of the cost of our gold electrodes. And really it comes down to gold is a highly expensive material. So there's a kind of, there's a dichotomy because everyone, is developing sensors, developing assays, and often, you'll see in the title of the paper, low cost, sensor for. And gold and low cost just do not go together. This is a luxury material that's used to kind of hold wealth. It's traded as essentially as a wealth asset, and then we're competing for that material when we try to combine it into electrodes. So I would really say that building assays and thinking that you're making a low cost assay when you've got gold intrinsically tied up in that assay is not going to lead to low cost. Whereas if you actually look at carbon, mass for mass is 1/28,000th of the cost. It's a hard term to say, but 1/28,000th of the cost of gold. So carbon is a commodity material. It's sort of can be found at higher volume. You're not competing with people trying to kind of trade carbon the same way that they trade gold. So carbon is just a low cost material. Now, some other comments about gold. It is prone to fouling. If you go kind of anywhere, where they've got gold objects, of course, one of the things that people do with gold is they polish it, and over time it gets dulled, and it's basically absorbing materials from the atmosphere. I would actually, and I've realized this now, that actually carbon is actually quite resistant to fouling. It's not absorbing thiol molecules from the atmosphere and necessarily tarnishing. Just FYI, when we are using carbon or gold electrodes in building biosensors, we do use an activation step as part of our manufacturing. So we do actually clean them. So we do clean both. But gold has this kind of considered this inert material. But relative to carbon, I'd actually say that gold is actually less inert than carbon. And that really comes up on the second point here, that anyone who's worked with a gold electrode, that in some environments, some liquid environments, actually gold is quite easy to strip. You're increasing the positive potential and suddenly you get this kind of stripping potential. And then you may come back if you're doing cyclophotometry and you'll get this deposition event. And so you're sort of stripping gold and making the kind of gold 3+ ion, and then you're plating the gold 3+ ion back onto the electrode. So it's not the electrochemically stable material that people necessarily think it is. Whereas actually I'd argue carbon's got a much wider window of electrochemical stability. We can apply higher negative and positive and negative potentials, and actually carbon is inert. One of the advantages of gold is you can easily modify it with thiols. So earlier on I kind of put that as a disadvantage because it will absorb sulphur molecules from the atmosphere. The same means that you can also use thiols in terms of making self-assembled monolayers, which I'll get to in a bit. So it is easy to modify. But I would also say that carbon is actually just as easy to modify as well. You see plenty of papers where they take the carbon surface and they oxidize it so it's got some more oxygens on the surface, and then they use things like EDC, NHS coupling. They make, they can couple to the surface using amide bonds. We've used pyrene NHS a bit. Pyrene is quite good because it's got 4 aromatic rings, so it stacks quite well on top of a graphite surface. So I would actually argue that gold has historically been used because it's easy to modify primarily through these thiols, but actually carbon now, there's just as much literature coming up on carbon. And of course, you just have the real advantage of actually the low costness of carbon versus gold. One thing I have noticed a lot, mechanical stability. People, are making kind of gold electrodes on polymers. They're making gold electrodes on glass. Maybe I'm talking a little bit more about sort of vapor deposition techniques here, but these electrodes do delaminate. They're not exactly robust, whereas at least the carbon electrodes that we make are really robust. You're somewhat hard to scratch these kind of surfaces. So I'd actually argue that carbon is actually quite robust material. And in fact, I do have videos online where we show you how to clean these electrodes so you can actually reuse them as well. And the cleaning is it's just a simple acid, voltammetry and acid. This is a true statement actually, that when you try to modify gold electrodes with mediators, I found those to be quite the surface that mediator is, essentially you're sometimes doing voltammetry, so the mediator is kind of being put down by electrochemical deposition or electrochemical polymerization. It doesn't have a great adherence actually to gold because it can tend to be a bit smooth, whereas you will get good adherence or compatibility with mediators when it comes to carbon. Especially many mediators are actually organic in nature, so they have a tendency to kind of pi stack with carbon surfaces. Best use case scenario for gold is self-assembled monolayers. So there is plenty of literature out there. It is a robust piece of science, and that's what's probably leading a lot of people to gold. But it's become the kind of default material. But it absolutely is going up in cost. It's tripled in price in the last 5 years. And I would actually argue that carbon, you just have to look at your assay a little bit, rethink it a bit, and then actually it's just as good as gold when it comes to doing electrochemistry. This statement here that gold can be variable, it's true that gold can be variable, whether, carbon can also be variables. It's really about your manufacturing, and it's something that we really lean upon. Now, there's an economics here that actually, because at ZP, we promote carbon over gold because actually it leads to a low cost sensor, it leads to a low cost assay. That means then that we got more people buying carbon off us, which means that we're actually making higher volumes of carbon versus gold. And therefore, the more you manufacture something, the more regularly you do it, it actually impacts on the quality. So actually, in our particular case, I would argue that carbon electrodes, because of their higher volume, which is driven by the lower pricing, actually leads to a higher quality per electrode. Now, what I want to do now is just kind of illustrate some uses of carbon electrodes. I'm going to touch on just doing simple electrochemistry on a carbon electrode, and I'm going to also touch upon doing a real-world assay on a carbon electrode. So let me just change cameras for a second. I'm just going to take this electrode out, easy enough to just snap that down. I'll put one of our 501s in here, snap that in. I'm just going to get my phone because my phone's in Bluetooth connection with the potentiostat. So I'm just going to take a 5 millimolar ferricyanide solution and just do a quick piece of voltammetry on that electrode. So 5 millimolar ferricyanide here. Right, I've grabbed the 5 millimolar ferricyanide. I'll put it on. I'll just make sure I name it in the app so I can actually find that data. Ferricyanide demo, so I can find it quite readily. And I'll go continue. I'll start at minus 200 millivolts. I'll go to 600 millivolts. I'll go to scan rate quite fast. I'm going to do 3. We say repeats here. I suppose in 3 cycles. I'll set the current range to 100 microamps and I'll hit start. So just to kind of show, that carbon electrodes, they're perfectly functional. They work with materials like ferricyanide. I'm just going to do 3 cycles here. I know I'm scanning at 100 millivolts per second because I know I say it in my videos, but in the end, people want fast assays. Generally, people are using carbon and gold electrodes because they're doing assay development. And what those real end users, those doctors, those nurses, those food technologists, those environmental scientists, what they don't want is beautiful voltammetry. What they actually want are assays that work and that they work at speed, because people have to get on with their other jobs. They don't want to be hanging around, let's say, for our assays to finish. So I've just done 3 scans there. It'll come to the end. It'll upload the data, and then I'm just gonna go up to the cloud and show you the data up there. So that's me doing a quick piece of voltammetry on ferricyanide. I'm just gonna navigate to a server that we've got called jewellery, and then I'll be able to, if I share my screen here, screen 2, yeah, and then I'll just do a quick refresh. I'm just going to jump in there and take a quick look at scan 2 of those 2 scans, so it'll load up. So the nice thing about this potentiostat is everything immediately goes to the cloud, and I can start analyzing it, grabbing data, etc. So carbon, this is the use of a carbon electrode in this particular case on ferricyanide. Here it comes, and what I'm going to do is I'm just going to grab the second one here. So what I'll do here is just go to Tools, go to Properties, just drop down this, go to here, delete that, and then I should be able to see the second scan singled out. This is a very powerful system for essentially turning electrochemical data like voltammetry actually into something meaningful. So in this particular case, let me just do something with this data just real quick, which I want to do for you. So if I go Tools, I'll do find the peak height. That peak height is probably around 300 millivolts. I'll do a window 100 millivolts. I just want to have a look what that looks like. So the good thing about carbon screen bridge electrodes is they can bring you to an assay quite quickly and bring you to an economic assay quite quickly. So there I found the peak height. Now what I want to do is I just want to guess some calibration factors. So let me just try something now. So Tools, by the way, the only way you can get away with global calibration the way I'm going to do this is if you've got repeatable screen bridge electrodes. What's holding back so much development is screen bridge electrodes that are on the R&D market effectively not reproducible. It's a bit of a, yeah, it's just a problem basically. I'm just going to put 10 in here. I'll just put in 0 here. Bear with me so I'm putting some global calibration in, assuming that all my electrodes are repeatable. Now with ZP, we can make that assumption because we're making them at high volume, because the low price drives the high volume. And here I've got 1.68. So let me just drop, well, because I know the solution is 5 millimolar. With my calibration that I just guessed at, I got essentially almost 2 millimolar. So I just want to decrease a value a little bit, and then I'll just show you that you can actually start tuning. You can basically do a calibration curve, find the global calibration, and then apply that, and you'll find out then that you, rather than leaving your kind of end user with all this voltammetry, you can actually leave your end user with a concentration. And I'll do one more adjustment of that, and then I'll go on to do an actual I'll do a second demo in a minute. So let me just go 3 on that, and here it comes. So this is a cloud system that talks to that particular potentiostat, and there we are. So 5.599. I won't tune it anymore, but you can see that actually we can go from peak height to concentration, and in this case the real concentration is actually 5 millimolar. So I can tune that global calibration and actually get that correct. But what I want to do is actually just do a second demo for you. It'll be the same instrument. So let me just go to the screen, and what I'm going to do is I'm just going to scan a new QR code. So I'll just open up the app. So I got the app here. I open up this. I scan that, and now I'm into what we call caffeine mode. Now the only reason I can do this is because, well, this wouldn't be an economic thing to do if we made it from gold. It would actually be too expensive per test, and it's also the reproducibility of our electrodes that allows us to do this. So I'm just going to take that electrode out. I'm just going to put in an electrode now. So the electrode goes in, job done. What I want to do now is just go to here. I've actually got some Red Bull in front of me. I realize I should have brought the can, but the can's somewhere behind me. So I'll just put Red Bull demo, come back slightly. Right, so I'm going to just prepare the sample really quickly, but this is in Bluetooth connection. I've put the name Red Bull in here. because what I want to sort of demonstrate here is, I mean, when ZP talks about carbon being a platform for making low-cost sensors, if it wasn't, the assay that we've got here just wouldn't be economically viable. You can appreciate that people don't want to spend a lot of money measuring caffeine in energy drinks. So let me just take 50 microliters of Red Bull. Let me just take 50 microliters of a proprietary buffer that we actually ship with this kit. I realized that the amount of buffer that we ship with this kit, because electrochemistry allows you to only use 50 microliters, we can only need 50 microliters to prepare this sample. It means that somebody can get 10,000 tests out of the buffer that we actually ship with this kit. So that's a good sign for electrochemistry. Electrochemistry doesn't actually need a lot of samples. And I've put the sample in there. I will put the sample onto the sensor. I only need 50 microliters. So I will press continue, start measurement. And so now the potentiostat in this particular case now is actually recording square wave voltammetry. But because of that feature I showed you in the software earlier on, we're actually, in the cloud system that is, we can actually analyze the peaks and turn the peaks into something meaningful. That big peak you just saw appear there was the caffeine peak. And then it's giving me the result back. You can check this out on the internet, but that's the caffeine content for Red Bull. So now what I want to do is I just want to share very quickly with you here. So I'll just go back, whoops a daisy, I'll just share my screen here. I'll just go okay because the session timed out, but no real issues. I'll go to reports and then I'll just do a quick refresh here. So there's my Red Bull. So the reason I'm doing this is because people are trying to develop low-cost assays, and they're trying to sometimes do it upon gold. So I think my biggest gripe with gold is it's always going to be an expensive material. I mean, through the ages, people have always loved gold and want to use gold in jewellery and trade and coinage, etc. So, the gold is an expensive material, and you're never going to make a low-cost assay using gold. But in this particular case, what I've shown here is actually we can make a carbon assay, and we can make a carbon assay then at the right price. So this is the signal for caffeine. So let me just do essentially a summary, and the summary is quite simple. Gold and carbon, technically gold actually doesn't overall have some amazing property that makes it that much better than carbon. Either one will work in many applications, and if you think that it's the self-assembled monolayers of gold that make gold unique, no, you can also make monolayer constructions on carbon as well. The thing that really is it's more like a negative for gold, it's expensive, and I think people are starting to have to recycle gold electrodes, and you should always recycle, but they're really economically forced to recycle gold electrodes, especially in R&D. You can recycle carbon electrodes. I do have videos about how to clean carbon electrodes, and the carbon electrodes that we sell are just a fraction of the cost of the gold. Why? Not because we're greedy, it's just that gold is expensive and the materials that we use to prepare gold electrodes are just going up. Now, if you do have any questions regarding any of this that I've talked about today, don't hesitate to reach out to us at ZP. Okay, thanks very much.